Good evening. This is part 2 of our discussion about control charts. One of the main and most important of the 7 quality tools. If you're studying for your certified quality engineer, certified quality technician, or similar exams through ASQ, this is going to be one of the main things. It'll definitely be on the exam. Understanding what it is, how to create them, how to interpret them will be key for that test and for working in industry. So if you didn't see the first part of this video, you might want to back up and take a look at that. In it, I was talking about control charts and how it relates to things like run charts and SPC charts. And this is just my way of thinking it. A control chart is a run chart plus statistics. So in the first part, we developed the run chart, which is the structure, the framework here. We talked about recording values. We were describing a heat treating process. So we're measuring the hardness of samples out of a heat treating process. It could be any process though. And we're recording the results of those over time. So the horizontal axis in this case, and in many cases, represents what we call the independent variable. In other words, it's independent. Time is independent of whether we're heat treating or not. So this is independent. And the horizontal axis, if I have enough room there, the vertical axis, I mean right here, is the dependent. This dependent variable is really the one that we're interested in most. But the run chart, so the run chart plots the dependent variable over the independent variable. So the dependent is the result of the process. So from our last video, you can see I entered all of our values into an Excel spreadsheet, and we talked about plotting the X bar values. So as we look at our data table down here, this we might refer to as X1, X2, X3. If you remember from last time, we're working off a control plan, a quality control plan that dictates that we draw 3 samples per hour. And these are the hours of our day, hours of our shift, first, second, third, fourth, fifth hour. And this is a hardness. We talked about a normalizing furnace or a hot roll bar process of some kind. And there's a specification that we're comparing our process against. So maybe our customer has a print specification, and in our example, we said it was 88 plus or minus 5 points. And we were using the scale HRB, Rockwell Hardness B. This is just a common measurement scale for the hardness of moderately hard steels. So we're looking at our run chart, and we constructed this run chart. So we have 93 and 83. That represents, back here from our specification, 88 plus 5, 88 minus 5 is 93 and 83 respectively. So that represents, let me change colors here, our upper specification limit, lower specification limit, LSL, USL. These are important abbreviations in SPC, statistical process control. So, excuse me, so we have X1, X2, X3. Those are the 3 samples that we drew in our first hour, second hour, etc. We take, what we're plotting here is the X bar. Bar indicates average, so it's the average of these X values. And as you can see, and I just did all the calculations in Excel, the average of these 3 numbers is 88.5. So I took the 88.5 and I plotted it on my chart. And this is a run chart, but we're plotting the X bar values. So frequently you'll hear this referred to as an X bar chart. So this is a run chart. We're plotting the X bar values, and then we're adding statistics to it. So it's an X bar control chart. So we have X bar here, and now here's another important value that I'm going to introduce here. And in SBC, this is called the R, or the range. So this is the range of our values of our sample sizes. This, so we can see here 88.7 is the highest value, 88.3 is the lowest value. The difference between the two is 0.4. So 0.4 is our range. The range, or the R value, is pretty much the easiest measurement of variation in our sample size. So we performed the same process across 20 samples. We have 20 X bar values, 20 R values. This is just a rule of thumb for quality engineers, quality technicians. If you're a statistician or you're deeper into statistics, you may have a differing opinion, but the rule of thumb that I've gathered from quality textbooks, the Indiana Quality Council, Duran Quality Handbook, there's other standard quality practitioner texts out there. The rule of thumb is minimum 20 to 25 samples or subgroups. These are called subgroups. So you need a minimum of say 20 to 25 before you calculate your control limits. Control limits, I mentioned here statistics, control limits is what makes a run chart into a control chart. So we're going to talk about control limits right now. Let's look over here. I calculated a couple things here, and I just did this in Excel offline. I just realized I forgot to connect my last dot there. So there's our run chart. Okay. So what do we have over here? We have this value, which is the average of all my X bar values. So it's X bar bar. That's usually called X double bar because it's the average of the average X's. So the term is X double bar. This term right here is the average of my R values. So it's R bar. So I have X double bar and R bar, 86.2 and 0.6 are my values for that. Okay, so here's why that's important. I'm going to just leave it right here. Let me slide up a little bit. And I'm going to give you two formulas right now. Let me erase this stuff. I have a table. We're going to talk about this in a second. Pardon me. So our equations, we have two equations here for the upper control limit, sub X bar, and the lower control limit, sub X bar. Now this is not the specification limits. These are different things. These are called control limits. So we have some formulas I'm going to give you here in a second. Our upper control limit is the X double bar plus a value we're going to call A2 times R bar. Lower control limit, very similar, X double bar minus A2 times R bar. Let's calculate these first, and then we're going to just do a little bit of interpretation. So we can put in our values. So we know already our X double bar is 86.2 plus, in fact, I'm just going to do that right here, 86.2 minus, okay? Now what is this A2? There is a table of control chart constants. You can find this, I don't know who originally published it, but groups like the AIAG or Duran's Quality Handbook, really any standard quality engineering textbook or guidebook is going to have this in it. It's standard stuff. Again, if you're a statistician, you may know the derivation behind these. If you're a quality technician or studying for your quality auditor's exam, all you need to know is how to use this table. You don't have to know what's behind it. So let's take a look here. Table of control chart constants. And our formula for the upper and lower control limit on the X bar chart is calling for A2. So we have an A2 here. And then our rows are based on the subgroup size. We've called this the sample size or the subgroup size, very similar terms. In our case, the subgroup size is 3, or the sample size is 3. So if we slide over, we can look at the A2 value, 1.023. So that's a factor that's used to multiply. It's used as a multiplier of our R bar value of 0.6. Let me put a point there. 1.023, and this is times 0.6. So if we do our math really quick, and this is just about 1. I've done the math offline. So basically 1 times 0.6 is 0.6. So our upper control limit is going to be 86.8, and our lower control limit is going to be 85.6. Did I do my math right? 85.6, 86.8. Okay, so that's our upper and our lower control limits. This 0.23 probably drops off and becomes non-significant. So now we're going to plot our control limit lines and turn this run chart into a control chart. So our upper control limit, 86.8, 86.8, right about there. I'll run this off here. So that's our upper control limit. Lower control limit, 85.6, right about, how's that? Oops, made a mistake there, hit the wrong button. 85.6, right about there. Okay, so let's just label this here. Upper control limit, lower control limit. So we've done the calculation here, and we see our control limits are narrower than our specification limits. That part's good. But we also see that most of our points, not all of them, but many of our points are outside of the control limits. Even though they're inside the specification limits, they're outside of our control limits. Generically, we call this term out of control. So if our process were running like this, like what we're looking at, we could describe this as out of control. So in the next video, I'm going to dig into the interpretation of what we have. Right here, we've done the math. We're going to take a look at the interpretation and try to understand what all this means from a quality engineering perspective.